Hello student, in this video I am going to discuss about an example that is about evidence leaps from Facebook likes. So what type of evidence we can understand from the Facebook likes through business analytics point of view or data science point of view. Let's examine some evidence leap from real data to freshen up things up a little. Let's consider a brand new domain of application. Researchers Mikkel Koscinski and David Stilwell and Thor Grappel recently published a paper in 2013 in Proceedings of National Academy of Sciences showing some striking results. What people like on Facebook is quite predictive of all manner of traits that usually are not directly apparent. So those authors try to find out whatever evidence find from or whatever people what actually people likes on Facebooks, and when they press the button like, and they try to find some predictive pattern, like how they score on intelligence test, how they score on psychometric test, or how extroverted or conscious they are, whether they are gay, whether they drink alcohol or smoke, their religion, political views, and many more. This type of information can be extracted by seeing the behavior of liking in the Facebook pages. So that type of study taken out by these researchers. So that is predictive. This type of things can be predicted by analyzing this type of or this liking information in the Facebook. We encourage you to read the paper to understand their experimental design. You should be able to understand most of the results now that you have read this book, because you are going through this data science techniques, so you might understand the paper. So for example, for evaluating how well they can predict many of the binary traits, they report the area under ROC curve, which you can now interpret properly. What we like to do is to look to see what are the likes that give strong evidence leaps for high IQ, or more specifically more for scoring high IQ on an IQ test. Taking a sample of the Facebook population, if we define our target variable as binary variable, that is IQ greater than 130, about 40% of the sample and is positive, has IQ greater than 130. So let's examine the likes that give the highest evidence leaps. So some Facebook page likes and corresponding leaps. So leaps here is like a value. So leap for Lord of the Rings, like leap value is this much. So in that way you can see for different types: Lost, Lie to Me, How I Met Your Mother, Doctor Who, House, Moving Castle, The Godfather. So for various thing the leap value is associated. So recalling equation 9.4, equation 9.4 is probability of A as a product of evidence leaps. So we try to go through this equation to understand. Actually this is nothing but posterior probability or probability evidence lift. How we can calculate that? Lift as a metric of evaluating a classifier. Intuitively, lift is the amount by which a classifier concentrates the positive examples about negative examples. Lift measures how much more prevalent the positive class is in the selected subpopulation over the prevalence in the population as a whole. So here actually they use the naive based assumptions. Slight modification to with slight modification we can adapt our naive base equation to model the different leaves attribute. Like here you can see becomes the following for naive base: PC given E, evidence is given, then what is the C value? So P E1 C, evidence of E1 given C, evidence E2 given C, like that, divided by probability of evidence, probability of evidence 1, probability of evidence 2, like that. The terms in this equation can be arranged to yield this equation, that is probability as a product of evidence leaps. So we can see when leap Cx is defined, here. Leap Cx means probability of x given C divided by probability of x. consider how we will use our Bayesian classifier to classify a new example E, which that evidence samples are like E1, E2, Ek. Starting at the prior probability, each piece of evidence, it feature Ei raises or lower the probability of the class by a factor equal to that piece of evidence left. So actually this is the evidence, or if this value can be created for any evidence of a subpopulation. So that is what this value can be generated for any evidence of the subpopulations. So using that equation, independence assumption made, we can calculate the probability that someone has very high intelligence based on the things they like. If I like nothing, then my estimated probability of IQ greater than 130 is just base rate in the population, 14%. What if on Facebook I had liked one item, that is Sheldon Cooper, then using equation 94 my estimated probability would increase by 30, because 0.14, that is the base probability, into 1.3, that is 18%. If I have 3 likes Sheldon Cooper, Star Trek and Lord of the Rings, then my estimated probability of high IQ increases to 0.14 into 1.3 into 1.39 into 1.69, because 0.14 is the base value of the probability of having the IQ greater than 130, and multiplying with the leaf values, that is 1.3, 1.39 and 1.69, which become 43%. So of course there are also likes that would drag down my probability of IQ, so as not to depress you, you won't list them here. But you can see, suppose if you multiply with some low values of leaf value, then if you multiply with 14%, then that value will decrease, so you might get decrease in the base of IQ. So this example also illustrates how it is important to think carefully about exactly what the results mean in the light of the data generating processes. This doesn't really mean that liking the Lord of the Rings is a strong indication that I have very high IQ. It means clicking like on Facebook page called Lord of the Rings is a strong indication that I have very high IQ. This difference is important. The act of declaring publicly that you like something is different from simply liking it, and data we have represent an instance of a former and not the latter. So that is what you need to understand. But anyway, we can some predict, or we can some provide some indication about that IQ, but that might not be exact true. So evidence in action targeting consumer with ads, in spite of math that appears in these chapters, the calculations are quite simple to implement. So you can go through this chapter to understand this type of concepts, how we can use actually the concept of probability and concept of Naive-Bayes theorem, applying Bayes rule to data science. You can go through this. This is very important one in case of classification using Bayes rule. Using this uses actually probability, posterior probability. Okay, and you can go through the concepts relating to this, advantage and disadvantage of Naive-Bayes. You can find this in this book. Try to go through it, as we have gone through this example. By using the leaf value, we can predict some IQs of persons, or any other different traits of a person, like if their religion and political views, or whether they drink alcohol or smoke, like that can be predicted, or can give some indication about those study. So that you can also study this paper, where you can find how they have designed the experimental procedure. So try to understand this, and this might help you in case of understanding, or in case of analyzing any data in today's world, to classify or to understand data science using Bayes theorem. So that is all about in this video, just giving a brief hint about Bayes theorem and the example itself. So I advise you to go thoroughly about this Bayes theorem. It is very, very important. So if you have any doubt, please let me know. I'll try to resolve it over Google Meet. Or if you want to add anything with this, you can let me know. And in the next class, we'll try to go through regression. So that's it. Thank you.